So good morning and welcome back. Today we'll turn to a topic of the utmost importance in theoretical physics, but also for our further development of differential geometry, and that's Lie theory. So we arrived at chapter 4. Lie theory. Now, from the point of view of differential geometry, what we start with is Lie groups. You may have met or not met Lie algebras in physics, but we'll start with Lie groups, and once you start with a Lie group, to a Lie group there is an associated Lie algebra. So the question is, what is a Lie group? Well, that's a very simple one. And you certainly met several Lie groups already, maybe without knowing it. The definition is the following. A Lie group consisting of a set G and a group operation blob. A Lie group is, first of all, a group. With the group operation blob. And that means that the group operation blob satisfies the properties A and I. So blob is associative. Blob, there's a neutral element in G such that that neutral element blobbed with any other element yields that other element again. And there's an inverse element for each element in G. There is an inverse element such that taking the element and blobbing it with the inverse, you get back the neutral element. That's a group. And only sometimes is there also a commutative law, but that's a special case. That's then a so-called commutative or abelian, so that's just the same, it's just a synonym, or abelian group. So nothing spectacular about this. A Lie group is a group, but it's more than a group, because in addition, this underlying set G is much more than a set. G is actually a smooth manifold. That means there is a topology given on G and also a smooth structure, so a maximal smooth atlas. G is a smooth manifold, and that's not all of it, and these the operation, well, the blob operation, we can encode this in a map. And the maps, there are actually two maps we're considering, and the maps, the first one, we call it mu, like multiplication, mu that takes a pair of elements in G and sends it to G, and does so, G1, G2, by sending them to the blob product of the two. That's a map, and that's just a group operation. But now if G is a smooth manifold, then you can actually make G cross G is then clearly also a topological manifold, but you can also inherit a smooth atlas. So inherits a smooth atlas from G, because G has a smooth atlas, so you can equip the Cartesian product of the underlying topological manifolds again with a smooth atlas, with the result that the little cloud here is again a smooth manifold. Now, if this is a smooth manifold and this is a smooth manifold, we have a map mu between smooth manifolds, and this map mu can be, we can stipulate or require to be smooth. And the maps mu and I give you another map I want to be smooth, and the map, let's call it I, like inverse, that takes an element of G to its inverse, so takes an element G and maps it to G inverse, whose existence is guaranteed by this axiom, and the maps mu and I are both smooth maps. So in a sense, it's to be expected if you have a group and then you have extra structure on the underlying set, you want a kind of compatibility condition with that extra structure, in this case a multiplication or a, well, that's just a generic name for this blob operation, and you want that to be smooth as well. And so here this inverse, of course, is also an operation we'll use a lot, so also require that this be a smooth map. And any such structure with this combined properties is called a Lie group. Okay. Now, examples. Well, a very simple example is as G, you simply take R to the n, but because we want to construct a Lie group, we take Rn considered as a smooth manifold. And we know there is a topology understood and there's a smooth atlas understood. We suppress that in the notation, consider it as a smooth manifold. And as the blob operation, we simply take the addition on Rn. So you compose two elements in here by simply adding them component-wise. Now, this makes this, G with the blob, makes this a commutative Lie group, because the addition and the inverse, which is of course taking the opposite vector, are smooth. And sometimes one calls this the translation group, called the n-dimensional translation group. And when you studied quantum mechanics, you talked a lot about the momentum operator generating translations, right, of the wave function. Or even in classical mechanics, you take the Poisson bracket, you plug in into the first slot, you plug in a momentum, roughly speaking, and you act with this on other observables. Well, this commutator p comma dot also generates translations, and we'll find out that these generators I'm talking about, they actually belong to the Lie algebra. But the result, if you do this for a finite amount, that is what this translation group does. It shifts you. Okay? Of course, this we're not talking about the action of this group on some space. We're just talking you have a translation, then you have another translation, and you execute them one after the other. That is, you compose them here with the blob. And of course, you do this by shifting first in this direction, then in that direction. But you could have first shifted in that direction and then in this direction, right? So that's the translation group. So it's a Lie group because the underlying set is not a discrete set. Well, it's certainly a smooth manifold. Okay. Now, the second example is also a famous group you've met certainly in quantum mechanics. We call it S1. So you saw that before. That's the circle. But now I understand the circle as a set of points, but as a manifold it's the same, as all those complex numbers z whose absolute value is 1. So we're talking about the unit circle in the complex plane. Okay? And so this is, yeah. And the blob operation here is now supposed to be the multiplication on the complex numbers. Now you know that if you take two complex numbers lying on the unit circle in the complex plane, then multiplying them multiplies their radii, but they're 1. and it adds their angles. So if this was an angle phi and this was an angle psi, then the sum of the two is here, that number with angle phi plus psi. And you easily see that with this multiplication, everyone has an inverse, and then you go back and forth, and so on. And so it follows that S1 with this, well, I should have written here Rn with its addition, Rn is the translation group, and S1, consider this subset of the complex plane together with the multiplication, is again a commutative Lie group, again the special case, and this is usually called U1. It's the U1 group. That's the group that gives your, well, under which you construct your wave functions to be invariant, because the, well, at least the final results of calculations in quantum mechanics, you want them to be U1 invariant, because you don't want an overall phase to count. Now, so you met this group before. It's a very simple one. Okay. Now, as a final example, we may consider as the space G all the linear maps that take you from Rn to Rn, but that have non-vanishing determinant. This, of course, means that these linear maps are invertible. So I should emphasize here this is supposed to be linear maps that are invertible, and that set has a special name that's called GLN over R. That's the general linear group. Well, it's not a group yet, that's only a set. And if the blob operation is chosen to be the circ, the composition of maps, then certainly I can compose one map with another one, and because the determinant of the map is non-zero, there always exists an inverse, and the identity map is the identity of the group. So we have GLNR equipped with the composition is now that's no longer a commutative Lie group, because phi after psi is not generically the same as psi after phi, is a Lie group called the general linear group. And as such is also called GLNR. Okay. So these are all Lie groups. Well, if you have an inner well, let me give you one more example, because it occurs so often, but then that should be enough. So assume you have an inner product on an R vector space. So let V be a d-dimensional R vector space equipped with an inner product. Well, let's take a pseudo-inner product. Pseudo-inner product. Now, what's a pseudo-inner product? Well, a pseudo-inner product is a map that, a bilinear map that takes you from two vectors to the real numbers, all right, that satisfies well, first of all, it's bilinear. Okay, let's emphasize this again. It's already clear here. It's bilinear. And then it's non-degenerate. It's symmetric. Let's first say it's symmetric. That means you have VW is WV. Well, that should say for all VW in capital V. And the third property is that it be non-degenerate. And non-degenerate means that if for all W in V, it is true that V comma W is 0, then it's already true that V must have been 0. That's non-degeneracy. And there is a stronger form of non-degeneracy, and that is positive definiteness. So let me give this as a remark. A stronger requirement than non-degeneracy is positive definiteness. And positive definiteness would replace 3, would make it stronger. Let's call it 3 prime. And that says that for all V in W, VV is always greater or equal to 0. And VV equals 0 already implies that V was the 0 vector, the 0 in the capital V, right? And in that case, if 3 is replaced by 3 prime, we call the whole thing an inner product. And the pseudo is owed to the fact that I weakened the positive definiteness condition to only a non-degeneracy condition. And then there's a theorem. There are as many different, there are up to isomorphism only as many inner products, well, pseudo-inner products, on V as there are different signatures. What is a signature? Well, that is the Sylvester classification of symmetric bilinear maps. It tells you that you can always bring the matrix defining, so that's the matrix defining the inner product. So if you choose a basis of V, then you can always find a basis, so I should say there exists a basis of V, such that the components of this inner product take the following form: 1, 1, and then come minus 1, minus 1, and all the rest are zeros, and the signature is the number of ones and the number of minus ones. That's the signatures P, Q. And of course, P plus Q must be the dimension D. Okay? And positive definiteness is the condition that the signature be D, 0. But in relativity, we need inner products that have signature 1, D minus 1. Hence, I generalize to this case. Okay? And then, that's the thing I actually wanted to write down, so let me squeeze it here. We can define a set S, we call it O of P, Q. And that's the following set. That's the set of all linear maps phi from V to V, but there's a particular condition on those, namely this map phi should leave the inner product invariant in the following sense, that you take phi of phi and phi of W, and you take the inner product, that this should be equal to the inner product of V and W. So the inner product shouldn't feel that you mapped both entries, and this should be true for all VW in capital V. Okay, so you take this set, and you can check that this is actually a subgroup of the general linear group of P plus Q, comma R. Okay, it's the R vector space. So again, the inherited group operation blob is again the composition of such maps, and these are called the orthogonal group. So is a Lie group, is a Lie, so O, P, comma Q with the composition is a generically not commutative, is a non-commutative Lie group called the orthogonal group with respect to the pseudo inner product bracket. Okay, for instance, O1, 3 is called the Lorentz group in relativity, or O3, 0 is just the rotation group. So you saw all of this before, but now it's recognized as a Lie group. Now, this general linear group, we saw it already in action, hiddenly, in differential geometry. Namely, if you go to a point in the manifold and you transform the coordinates, the components of a vector, for instance, you had a linear matrix acting. This linear matrix was invertible. That was an action of the general linear group. And we'll come back to this when we talk about the frame bundle and principal bundles. And I promised you, maybe you remember, that I'll give you a proper bundle definition of what a tensor density was, because otherwise that's kind of awkward to formulate what a tensor density is unless you use what we're going to develop, this bundle language of principal bundles and associated vector bundles. And Lie groups play a very important role in there, so there's also preparation for that. But you should have seen this before, and that should also provide some motivation. So any questions so far? Yeah?
Why is the general linear group a manifold? I mean,
Yes, that's a good question. So, okay, very good question. So why is this a manifold? Now, this is a map from Rn to Rn. And if we didn't have this condition here, this would, I'm now arguing quickly, but it's exact, quick but exact. These maps can, of course, be represented by Rn squared many numbers, namely the components of such a map. So R to the n squared is a smooth manifold. We now know how to make this to a smooth manifold. Now, this G isn't this, but it's this without all those matrices, n by n matrices, where the determinant is 0. But the determinant being non-zero is a so-called open condition. Well, why is it an open condition? Well, because what remains is an open subset of this. So you may want to write this like this. Supposed to say this is a subset. It's a subset. And if you make a little twiddle here, it's an open subset. Okay, it's an open subset of this guy. Now you have an open subset of a smooth manifold. You can think about the charts. You can think about the induced charts and so on, and topology, and then you'll quickly find that in this case this is really a submanifold of this smooth manifold, and so it's a manifold, a smooth manifold. Okay, but it's a very good question. So everything is clear up to this condition here, but then that the remaining stuff is open saves the day. So now, of course, for instance, the rotation group you might have met in the form that you provide 3 angles and you parameterize every element of the rotation group by 3 angles, right? But now, of course, you quickly realize, aha, this is a manifold, so of course I can choose charts. And what was always the problem with these angles in the rotation group? Well, that if you take theta to 0, you can use all the phi's, but you don't move from that point. So you said, well, that's a point you shouldn't look at. Okay, there's a problem there. And so, well, it's just a chart of the manifold. The group is a manifold, right? And you cover it by charts. And well, for instance, for the rotation group, you don't, say O3, you don't have a single chart covering it all. And what you always met these 3 angles is just one particular chart that covers some part of the group. So what's the problem with this point? Well, there's no problem. You have another chart that covers that part. You choose that appropriately, and there is nothing special about this point, right? So now by choosing charts, you go back to to the form of these groups you always saw, namely parameterized by some angles or something else. Okay, so actually nothing needs to be said there anymore, because as soon as it's a smooth manifold, you know, you can choose these charts. Okay, so this is understood, and I'll see whether I can provide a problem on the problem sheet with that. Now, we quickly move on to the next topic, and that's the Lie group of a Lie algebra. The other way around. The Lie algebra of a Lie group. So what's the Lie algebra? Well, we need some preparation. So first, definition. So let G, blob be a Lie group. Now, something very simple is the so-called left translation. Then for any G in G, for any group element, there exists a map. There is a map. Let's call it L, like left, and sub G, because it depends on the G. And it does something extremely simple. It maps you from the group into the group. And it takes an element H of the group, and it maps it to the element L sub G of H, and that very simply, and what else should it be, is G blob H. Then there is a map, called the left translation. The left translation with respect to G. Aha. So you see, again, it doesn't seem worth the effort to define such a guy, because we had this wonderful blob map, and all it says is fix the first factor of the blob map and see how it acts on any other element in the group. But this is a map from the manifold, smooth manifold, into itself, and we're going to use this left translation map. Now, we make the following observation, namely that each LG, the each referring to the choice of G, so whatever G you choose, each LG is an isomorphism. So why is this? Well, it's certainly injective. Why is that, or how do we check this? Well, let this LG act on an H and assume the result is the same as if it acted on H prime. Now, this, of course, is GH, and this here is GH prime. Now, because capital G is a group, for every element there exists an inverse. Therefore, well, if you wish on both sides, you can come from the left by the inverse, and you find H is H prime. So if the images coincide, and it then already follows that the points at which the map was applied coincide, then the map is injective. Now, why is the map surjective? So in order to check that, let H be any element of G. Well, G is the target, so let's take any element of the target. Now, why is any element of the target hit by LG? Then LG acting on G inverse H, which is clearly an element of G, is of course G inverse H, because the whole thing is associative, is G inverse H, is the identity H is H. So we hit any element of the target by LG, namely starting from G inverse H. So this is an isomorphism of the sets. Now, is it also a group isomorphism? Well, we have to check whether it's group isomorphism. Because we already have the bijectivity, we only need to check whether what happens to LG of H1 group operation H2. Right? So this yields G H1 H2. And the question is this the same as LG H1 blob LG H2? Which is GH1 GH2. Well, in general, it's not. Okay. Right. Okay. So we have that. Now, why do I insist on this being a... So it's an injective, it's surjective, but it's certainly a diffeomorphism between the underlying manifolds. But certainly LG, any LG, is a diffeomorphism from G to G, or we say on the underlying smooth manifold G. Okay. Not a Lie algebra isomorphism, because then it needs to be diffeomorphism and also a group isomorphism, but it's a diffeomorphism on G. Now, why do I insist on this? Well, recall that we could extend the pullback, which was defined for covectors at a point, to covector fields. Simply by saying we apply the pullback to every point of the manifold, of the target manifold, and we pull back the value of some covector field on the manifold. Okay? Now, unfortunately, or well, it's just a fact, that you cannot do the same thing for vector fields. For the push forward of vector fields, there is a problem. So that we could extend, I should emphasize here, without further or without problems, right? So we could go back to that lecture and look at that. But the push forward of a vector field of a vector cannot be extended to the push forward of a vector field. And now it comes unless the underlying smooth map which induces the push forward is a diffeomorphism. Is a diffeo. Now why is that? So it's important to keep this in mind, so I rather make a point out of it rather than hiding it in the formalism. So you have a manifold M and a manifold N in general. Well, here it's twice the same manifold, but that doesn't change the principle. And you have a map H between the two manifolds, right? Now H is a smooth map. H is smooth, okay, all right, but it's also it's a map. Now what is a map? A map assigns to every point here, it assigns a unique point over there. Is that right? That's a map. That's what a map does. That means every point in M has an image over here, although the image maybe doesn't fill all of N, right? That's what H does, right? But it's more than that. It also assigns to every point in M only one point over here. It doesn't take one point and takes it to 2 points. No, it doesn't do that. To every point here, it assigns 1 point here. Now for the pullback, that's fantastic, because that means if I have a covector field over here, right, I put a covector field omega on this N, what I can do, I can look at the omega at this point here, and I know precisely that I can take this one and I pull it back to an omega here, and although there's also an omega given here, that will never be seen by the pullback, because the pullback will only take the points in the image here and pull them back and fill all of this here with H pullback omega, right? Clear. Now, both the fact that every element is mapped on M and that it's mapped to exactly one thing. Now, think about the same situation, M and N. There's a map, H is a smooth map from M to N. But if you now think of the push forward, you have a problem. First of all, not every point over there is hit. If we take the same picture here, so I take every point here, right, of course, because it's a map, but only some region, namely the image, is hit. So from a vector field that's given here, you will never be able to define a vector field at that point by push forward, because none of the points here is being mapped to this point. Obvious. But it's even worse. It could be that this point here is mapped to this point, and that other point is mapped to the same point. That's if the map is not injective. It's a map, all right, but two different points go to one point under the map H. But for the push forward, that's another thing. So you could say, well, maybe I only want a vector field in the image. Well, but even then, if the map is not injective, this vector is pushed here, and that other vector is also pushed there, say it looks like this. So the push forward extended, if you don't look at one point to one point, then it's fine. But if you want to extend this to a vector field, it becomes ill-defined, because you don't know which of the images you should choose as the resulting vector field here. So you see, the problems that came up is, first, the map wasn't surjective, you didn't hit everything. And the second problem was, even if it was surjective, or you restrict to the image, then if it's not injective, you also have a problem of being well defined. Right? So exactly what the properties of a map is, everything is mapped to exactly one value. If you go the other way around, you need injectivity and surjectivity to make it work the opposite direction. But of course, injectivity and surjectivity is bijectivity, then there exists an inverse. Of course, that makes total sense. So if the map, so you cannot do this for vector fields unless the underlying smooth map is bijective and in both directions smooth. So in other words, unless it's a diffeo. So if the map is a diffeo, then also the push forwards of vector fields here will produce well-defined vector fields here. So what have we found? We found that on our smooth manifold G underlying the Lie algebra, there is, for any element G in G, I can construct a diffeomorphism that sends points of the manifold to the manifold. But because this is a diffeo, I can use the push forward of this map to map vector fields on the group to vector fields on the group manifold. Okay? So it's maybe a little abstract. What we're now going to consider next is we take our group, say the rotation group, which is a manifold in particular, and we'll consider vector fields on that manifold. You say, why on earth would you do that? Well, it will turn out that's the key to considering Lie algebras. Okay? Okay, so we have this LG, these left translations, they're diffeos, and because they're diffeos, we can extend the action to vector fields on the group. So upshot can push forward any vector field, any smooth vector field, that's understood, any vector field X on G to another vector field LG push forward on the vector field. That's not defined yet. We defined the push forward of a map on a vector, but not on a vector field. But I define it on the vector field at the point H in G. I define it to be the push forward of the vector field at the point H, and I think then I want here is the push forward at GH. Right. Okay, so that's just the definition. You see, this is a vector field. And the result is a vector field, and it's evaluated at GH. And this here is not a vector field, this is a vector in THG. Right? So this is just putting in formulae what I said before. I can now define the push forward of a vector field, pointwise, in this sense. Okay. Now, we're not interested in any vector field on a Lie group. We're only interested in a special class of vector fields, namely those vector fields that if I push them forward and I look at the result doesn't look different from the vector field I started from. Okay? So for instance, in the plane, we saw that R2 with the addition is a Lie group. Now, if I take what you would call a homogeneous vector field, you look at that, and now you do an addition and you push forward the vectors of this vector field by this addition, which is intuitively you push the vector field in this direction, or in that direction, or in that direction. And if it was a homogeneous vector field, after pushing, it will look the same. Okay? So a homogeneous vector field in R2 equipped with plus, making it into a Lie group, is a vector field that under left translations, or rather the induced push forward of left translations, stays the same. And the analog of this we want to consider on any Lie group, and those are the so-called left invariant, because nothing changes, the left invariant vector fields. So definition. Let G blob be a Lie group, and X a vector field on G, then X is called left invariant. It's called a left invariant vector field if for any G in G that I choose, the action of L sub G, which if it acted on an element in G, would just multiply it from the left by G. Very trivial. But that's a smooth maps, even a diffeomorphism from G to G. So I can actually apply the push forward that's associated with that. I can apply it to the entire vector field. And I require that the whole thing is again the same vector field. Nothing changes. It's left invariant. It's invariant under the push forward that's induced by the left translation. Now, that's the formulation as a vector field equation. So let me say here, this is the vector field equation, since on the left and on the right you have a vector field. Alternatively, and it's useful to write down two alternatives. Alternatively, one can write this using the definition of what the push forward means. One can write this as, well, it means you take the push forward of a vector field. Well, you take the vector at the point H. Take a vector at the point H and you push it forward, and the result is of course a vector at the point GH, and indeed you had a vector field, so you can also evaluate it at the point GH, and pushing forward the vector from H to this point GH, the result should coincide with the vector field that's already given there. Well, that's the same as here, but now it's a vector equation. Vector equation. Now, how can that be? Well, because now you've got to say for every H in G, this is true. It's just the same as here, but written pointwise. Okay? So that's one reformulation. That's very useful. And there's yet another reformulation. One can write it as follows. So we start from here. So we take the push forward of the vector field at the point H, and we know that ought to be the vector field at GH. Now, this here is again a vector at GH, you know, and this is also a vector at GH, makes perfect sense. But now we can apply it to an arbitrary function on F. So now we take an arbitrary smooth function on our manifold, G. And, well, if this is true for all the vectors, then it must be true that for all H's, H in G, and for all F in C infinity G, this equation is true. Right? It's just, if the vectors are the same, then the action on a function is the same. Okay? Right. Now, what do I want? Aha! Now we can use, on the left-hand side, we can use our definition of the push forward. What was the push forward? Well, the push forward took the vector I want to push forward, and it applies it to the function f, but it can't do so unless I compose it with the map, the diffeo in this case, that underlies, the smooth map that underlies the push forward. But that's the map LG, if the push forward is LG sub star. Well, that was the definition of the push forward. Definition of push forward. Okay, so we get this guy. And, well, what is that guy? Well, that's the vector at position GH acting on F. But there's no harm in letting the entire vector field act, but then only look at the result, evaluate the function at the point GH. It's also clear. But now I like to massage this one bit further, namely I say this is XF, and I don't evaluate at GH, but I want to evaluate at H, but then I have to compose this function with the function LG and evaluate the result at H. Okay? But the same trick I can pull here. Instead of letting the vector at the point H act on the function, I can let the entire vector field act on the function, but then I only look at the result at point H. Aha, but this is true for every H in G. That means this is equivalent to saying x of f after LG is XF applied after LG. So we have these three formulations, and this is true for all f in C infinity G. Well, the condition is that for all f it's true. So you have these three reformulations. So you see, you can also think of a left invariant vector field as acting on f after a left translation by acting only on the first, well, it's not a factor because it's a composition, but to memorize it, by acting only on the first f and ignoring the LG as far as the action of the vector field is concerned, this LG pulls out. Well, not every vector field will do this. A general vector field, if it acts on a composition, you need the product, the chain rule, right? Some kind of chain rule. Well, we wouldn't even know what that is here. But in fact, for a left invariant vector field, it's simple. You act just on the function, and then you put after LG back there without any further derivative. Okay? So that's a left invariant vector field. And we want to look at the set of all left invariant vector fields. So definition, well, the set of all left invariant vector fields on a Lie group G be denoted L of G. And so far, it's only a set. But you quickly observe that the addition of vector fields, so LG is certainly a subset of all the vector fields you can have on your manifolds. So of all sections of the tangent bundle. Remember, the sections of the tangent bundle are all the vector fields, right? It's clearly a subset because it's special vector fields, a vector field with a particular property, vector fields with particular property. Now, it's a subset, and this guy here is a C infinity G module. Now we remember that vector fields, that the set of vector fields doesn't necessarily have a basis. You remember the S2 where there was not even an everywhere non-vanishing vector field, much less was there a basis for the vector fields, right? C infinity G module, and this is a subset of such a module. The question is it not only a subset, but is it also a submodule? How do we check this? Well, we have to check that the addition that actually you can have on vector fields, that if you restrict it to LG, that it stays in LG, so that it's closed, that LG is closed under addition, and you have to check whether LG is closed under C infinity multiplication, S multiplication, but both of this, hang on a second, C infinity, well, that is not so clear. LG, no, it is, and why is it? Well, because the push, so the push forward is linear if it goes from point to point. The question is it C infinity linear? Is the push forward C infinity linear? Yes, it is, and you can see it from here, because if you multiplied this xh first by some function k, and then you apply the definition, then the k goes here in front, and the whole thing is, of course, the k pulls out. Okay? So in fact, this also closes, and because the push forward is C infinity linear, the push forward of a vector field. So that means that LG is a C infinity G module. But of course, without knowing anything further, we don't know whether this module has a basis. Now, you remember why we didn't want to consider the sections an R vector space. I mean, certainly the vector fields, they constitute an R vector space, right? That's trivial. And you say, well, why do we deal with modules if we could have an R vector space? Well, the point is, as an R vector space, it's certainly infinite dimensional, and the same it will turn out to be true for L of G. A priori, that could be the case for L of G, but it will turn out that L of G, which is in particular an R vector space, right? It is in particular. It will turn out, although this guy, the set of all vector fields, is infinite dimensional as an R vector space, this subspace LG will be finite dimensional. That we will prove now. And this LG will then be called the Lie algebra. But before we get there, we need to prove some more things. Let's first introduce some terminology. An abstract Lie algebra, and I call it abstract Lie algebra because this is true independent of whether the Lie algebra originates in a Lie group or not. So I could call this a Hodgson-Plots algebra, right? But we'll call it an abstract Lie algebra. An abstract Lie algebra, L plus dot bracket, and let me write another bracket than we used it so far. Let me write a double bracket. An abstract Lie algebra, L plus S multiplication double bracket is a K vector space. It doesn't matter whether it's real or complex. It's a K vector space, L plus S multiplication, equipped with an abstract Lie bracket, double bracket, that satisfies, so it's a Lie bracket, and what Lie means is that it satisfies, first it's bilinear, so that means that it takes two elements of the abstract Lie algebra and maps it to an element of the abstract Lie algebra. And second, it's anti-symmetric. Anti-symmetric, that means that it takes an x and a y, and that's the same as minus y comma x, so it picks up a minus sign. Because of bilinearity, it would suffice to require that x with x is 0, but well. And third property is that it satisfies the so-called Jacobi identity. And that's the following beast. So you look at nested brackets of this form where you have an element x, y, and z. So the second entry here is a bracket in itself. And to memorize this guy, you write down the same pattern 3 times and you add it. Okay, but now you cyclically permute, so you push everything x, y, z to the left, and what falls off on the left comes in from the right. So this is y, z, x, and z, x, y, and the result of taking the sum is 0, and that's the so-called Jacobi identity. And any such structure, K vector space with such a Lie bracket, is called an abstract Lie algebra. Example, taking L to be all the sections of the tangent bundle of some smooth manifold, any smooth manifold. This is clearly an R of a real manifold, is an R vector space. Well, we know it's even a C infinity M module, okay? But in particular, weaker structure is that it's an R vector space. All right? That's this L. And as the abstract Lie bracket, did I call it the abstract? Yeah, I called it the abstract Lie bracket. As the abstract Lie bracket, I take the bracket we defined for vector fields. You remember? So, bracket of vector fields. Now, is the bracket of vector fields bilinear? You say, no, it isn't, because what happens if I have an fx that is not linear? Well, it's bilinear in the vector space sense. So if I say here it's bilinear, then that refers to the vector space structure. So we're not talking about C infinity linearity, we're talking about K linearity, right? So this guy is certainly R linear or R bilinear. And I don't know whether we checked or I had you check or we forgot, but certainly it's anti-symmetric. It's obvious from the definition of the bracket of the between the vector fields, and it also satisfies the Jacobi identity. Okay, so what does that mean? Well, it means that the collection of all vector fields, which is a K vector space in particular, together with the commutator of vector fields that we had, is and in fact an infinite dimensional, not only an infinite dimensional vector space, but because it has this bracket, an infinite dimensional abstract Lie algebra. Well, it's not so abstract anymore because we now made it concrete. We constructed it, okay? It's an infinite dimensional Lie algebra. Okay? Yeah?
You cause some confusion by saying that R vector space is a weaker condition than
Well, it's insofar. Okay, you want to explain why it confuses you, or? Okay, good. So, okay, so if something is a C infinity module, you can take its elements and scale them with any smooth function, namely in C infinity of the manifold. A particular case of such functions is the constant functions. And the constant functions therefore mimic just multiplication by a number. Okay? So if I say something is closed, for instance, under multiplication by constant functions, that's a weaker requirement than requiring it be closed under multiplication by just any function.
R is weaker than C infinity, but vector space is stronger than module.
Yes, but only in, yeah, but you cannot compare. You could only compare if you could consider the vector space over the same type of object than a module, right? But that, by definition, is not well.
So it wasn't that very far.
No, it was supposed to mean that anything that's a C infinity M module is certainly also an R vector space if M is a real manifold. So can we believe that? So okay, a fact, yeah. Aside, if some object Q is some object, okay? If Q is a C infinity M module, and M is a real manifold, real smooth manifold, isn't it true that then Q is always an R vector space? I think it's pretty obvious, because this guy here is just a ring. Now, it's certainly, if you restrict the ring so much that it becomes a field, namely if you restrict this ring of all smooth functions to all the constant functions, then it becomes a field. So certainly Q, that's a C infinity M module, it implies Q is an R vector space. And you might not even be able to take an arbitrary Q that's an R vector space and scale it by a function. You're still in the same space. So the implication arrow is in this direction. So this is the stronger one than this one. In this sense, I meant, well, that is anyway, that is what I used up here. This is a C infinity M module, but it's certainly an R vector space. I mean, this is lots of terminology about very little. It's clear you could check from the beginning. You have vector fields, you can add them, and you can scale them by a real number. And the whole thing satisfies the axioms of vector space. So we don't need to come from the fact that this is a C infinity module to conclude it's an R vector space. We could check this directly. And nothing else I need. Okay? But I understand your question. But this is the sense in which I meant it. Okay. So, now what I would like to check, so this was a brief aside on abstract Lie algebras. Oh, okay. And what I would like to check is the following. Theorem. L of G, the set of left invariant vector fields equipped with the bracket on vector fields, which I can use because these are vector fields, so I can take their bracket, right, is a Lie subalgebra of gamma of Tg with that same bracket. Well, I know that L of G is a subset of gamma Tg, and I know that it's even an R subvector space of this guy. Now, what is it with the brackets? Well, this is the bracket only restricted to this, all right, but the question is, does the bracket close on Lg? So proof, it remains to be shown that if you take the bracket of vector fields, but you decide to feed into the bracket two left invariant vector fields, it remains to be shown that what you get is again a left invariant vector field. It could be you feed it two left invariant vector fields, but the bracket destroys this left invariance property, and the result is a vector field. It must be, but it's not a left invariant vector field, right? So we need to show that the result is again a left invariant vector field. So how do we do that? Well, we take the commutator of two left invariant vector fields. Okay? Now, we let it act on the following object, f after Lg. Why do we want to look at this? Do you remember that we saw that something that's in front of this is a left invariant vector field if we can show that the action on this guy is the same as if this guy acted only on the first function, and then afterwards there's the composition with Lg. That was the secondary formulation of left invariant vector field. Now x and y are supposed to be left invariant. We take them from here. So we take x and y to be left invariant vector fields. Now we need to show that the identity I just quoted is satisfied if x and y satisfy it. So how do we do this? Well, that works as follows. What's the commutator of xy? Well, that's x applied to y applied to the function that's given there. So it's this guy minus y applied to x applied to the function that's provided. Okay, that's the definition of the commutator. So definition of the commutator between two vector fields. All right? This equals. Now, we look at y acting on f after Lg. But y is a left invariant vector field by assumption, so we can let it act on f only and then compose with Lg. So it's x of untouched, but then because y is left invariant, it's yf after Lg. So this is because y is left invariant, right? Close bracket, minus, well, now we do the same thing with x, because x is also assumed to be left invariant, is x on f after L sub g. So this equal sign uses that x and y are left invariant. But now, what is the result of a vector field acting on a function? Well, it's a function. So we have again x acting on some function after Lg. But x is a left invariant vector field, so I can let it act only on the function and only then compose with Lg. So it's x of y of f, and only afterwards I compose with Lg. The same is true here. Minus y, I let it first act only on the function ff, xf, which is only justified because y is left invariant. And only afterwards I compose with Lg. Right? But that's simple, because this is nothing but x comma y acting on f, and then you have Lg. But this is precisely one of the conditions, namely the third condition, the third alternative reformulation of what characterizes a left invariant vector field, namely that you can let it act on f after a left translation, and that's the same as letting it act on f and only then composing with the left translation. That is xy is a left invariant vector field. on G. That finishes the proof, and it shows indeed the result is left invariant again. So you can also say LG, the elements of LG, the left invariant vector fields, they close under the Lie bracket, and that makes this a Lie subalgebra of this guy. But we know that as a Lie algebra, we just had it as an example, the vector fields equipped with the commutator bracket of vector fields is an infinite dimensional Lie algebra. The question is, what is the dimension of this LG? It's a subalgebra. Is it also infinite dimensional, or is it finite dimensional? And the answer is it's finite dimensional. Theorem. The Lie algebra L of G of a Lie group G is isomorphic as a vector space. You know, in particular, it's an R vector space. It's isomorphic as a vector space, and now it comes to the tangent space to the group at the identity element. E is the identity element of G. G is a group, so it has an identity element. So this LG, these left invariant vector fields, this rather abstract notion of a left invariant vector field, well, actually there are as many left invariant vector fields as there are tangent vectors to the Lie group at the identity. Okay, proof. Well, before we prove it, I can immediately write the corollary. So if this is true, if we're able to prove this, it follows, of course, that the dimension of the Lie group, the vector space dimension, is, of course, the dimension of the tangent space of the Lie group at the identity. It's, again, a vector space dimension. But that's, of course, the same as the dimension of the manifold, because the tangent space as a vector space has the manifold dimension of the underlying manifold. And, well, if this is a finite dimensional manifold, then the Lie group is finite dimensional. Okay? So that's the corollary. And now the proof. So what do we have to do? Need to construct a linear isomorphism. So a linear isomorphism is a vector space isomorphism. If you want to show that they're isomorphic as vector spaces, I need to construct that guy. Now, how could we call this? J. So I have a J. What does J do? J is supposed to take me from an element in the tangent space at the identity in linear fashion, meaning R linear fashion or K linear fashion, if we do what the complex numbers say, to L of G. I have to construct this guy, and I have to show that it's invertible, or injective and surjective. So how do I construct it? Well, let's take an element A. Let's say the Latin capitals are elements. It's just a vector in this tangent space at the identity. And so I send this to J of A, okay? But J of A is supposed to be a left invariant vector field. So I have to say how I construct this left invariant vector field from an element of the tangent space. Well, J of A is a left invariant vector field. It's a vector field in particular, so I can define it at the position G, and then it's a vector, right? So if I have a vector field and I evaluate it at a point, that's the notation we always used, then this guy here is an element of the tangent space at G, right? How do I construct this from an element in the tangent space at E? Well, nothing simpler than that. I use the left translation and I push forward the element in the tangent space at E. I push it forward using LG, if this was A was a vector in TEG, then this is a vector in T, so the element lies here in TGE, G, but GE is just TG. Ah, that lies in TG too, that's fine. And if I do this now for all G in G, I defined a vector everywhere on the group manifold. So think of, that's the group manifold, right? And I only give you a vector in the tangent space at the identity. Say that's the identity. What do? Well, I push this forward with respect to all possible LGs, right? And that way I get a vector everywhere. That's a vector field. Now, what I have to show, well, this is a vector field. Now the question is it a left invariant vector field? So far by this construction, I only argued that this is in gamma TG. But is it left invariant? So 1 is to show that J of A is left invariant. How do we do that? Well, now we use the second formulation we had is now the most convenient. I use LH, so I push it by an H, that doesn't matter. LH pushes the J of A, and I push the J of A at the position G, and I want to show that that is the J of A at position HG. So how do I do this? Well, I plug in what this is. This is LH push forward. Now this guy itself, right, as it's there, is the push forward LG push forward of a given A. Now this equals, and that I will show in a second separately, this is the push forward of LHG push forward H, and that's of course J of A at position HG. And if I can prove this guy here, so that's the only step that's maybe a little quick, then I showed that the push forward pushes you to this other point, so it's left invariant. Now the question is, why is this true? Why is it true that if I take LH star, LG star, and I let it act on an arbitrary vector field, or an arbitrary vector, let's do this in general, an arbitrary vector, why is this same as this guy? Well, let the whole thing as a result act on an arbitrary function. So I just want to check this for every f. What's the definition of this guy? Then the definition of this guy is, so I act on this one first. So I have to take the vector LG star, and I have to have it act on the LG star x, and I have to have it act on the function, but only after I used this map in front. What is this? This is the definition of the push forward, right? But now I can do the same thing again, because now I have a vector that I push forward. So I take the vector, I can let it act on the function that's there, but only, LH, but only after only if I compose it like this. That's again the definition of the push forward. No? So that's definition push forward, and that here is also the definition of the push forward. But now this is the composition of two left translations. That is, whatever comes from the right is multiplied from the left by G, and afterwards again multiplied from the left by H. Now that is obviously x of f after LHG. I can put these two guys together to this. So at the level of the push forward, that may be a little bit funny, but here it's clear directly from the definition. But this here is nothing, again, by the definition of the push forward, as L, H, G, push forward x applied to the function f. Aha. This is true for every function, so the composition, the composition in the sense of push forwards is the push forward of here a LHG. And that's what I used here. So certainly the JA I constructed there is a left invariant. So the second question, of course, is this map, I write down again because I had to erase it. So we were attempting to construct a linear map that's an isomorphism from the tangent space to the Lie group at the identity into the set of left invariant vector fields. And we already confirmed that indeed we do not only get a vector field by our construction, which was to assign to every a j of a, where j of a was a vector field defined by the push forward LG of this element A in TEG for all G in G. We already verified that this is not only a vector field on G, it's even a left invariant vector field on G. That was point 1. Now point 2, we want to verify that this is linear. Is R linear? Well, but that is obvious because you see LG star is R linear. So if I multiply this by some number here, then the number will jump right in front, so that will be the case. And it's also, because this is linear, it's also additive, of course. So A plus B leads to LG star A plus LG star B. So certainly it's R linear. So we didn't, so we in number 1, we verified that indeed the target is LG. And now in 2, we verified that in fact it's a linear map. It remains to be shown that it's invertible, so that's an isomorphism, or that it's injective and surjective. Now let's check whether J is injective. So what do we do for injectivity? Well, we consider the J of an A, and we assume it's the J of a B. And if we can show that from this it follows that A equals B, then the map was injective. So what is this? Well, this is equivalent. Well, no, it certainly implies, that suffices at this point, it certainly, so these are vector fields, right? Okay, so, well, let me do this in steps. This is an equation of vector fields. Now that means that at every point of the manifold, evaluating the vector field J of A at point G must yield the same result as evaluating that vector field J of B at G. That's clear. But now it only follows, but that's enough, that J of A certainly also at the identity is the J of B at the identity. All right? If it's true everywhere, it's in particular true at the identity. Now again, we continue with equivalence arrows. Now what is J of A at the identity? Well, it's L sub E push forward A, and that is supposed to be L sub E push forward of B. But what is the push forward LE start A? So of course the identity, this means this is A equals B. Aha, so J of A equals J of B implies, and it only implies it because there's only an implication arrow, that A equals B. But that's precisely what you want to show if it's injective, if it's supposed to be injective. So J is injective. And 4, we got to show that J is surjective. Now, how do we show this? Well, we have to take an arbitrary element in the target, and we need to show that it can be hit by the map. So okay, how could that in the target look like? Let X be any element in the target. So let X be a left invariant vector field. then define an A associated with this X, okay, to be X evaluated at the identity. So if X is a left invariant vector field, it's in particular a vector field. If it's a vector field, it has a value in every tangent space. It induces a vector in every tangent space, also in the tangent space TEG. Aha. So if I let AX to be that element that's generated from a left invariant vector field in the tangent space TEG, I have an element of TEG. Okay. Now I need to hit that element. Well, how do I know I hit it? Okay, anyway, I do this, and now I consider, my idea is that the J of this AX reproduces this X. JAX. So what is JAX? JAX at position G is, by definition of J, is LJ push forward of AX. Aha, yes, yes, of course. LJ push forward of AX, but that is LJ push forward of X at position E. But now I use that X is an element of the left invariant vector fields, so I know that this is the same as XGE. That was the second formulation of left invariant vector field, equivalent formulation, and that's of course XG. Aha. And that means that J of AX is X. The original, so I chose an arbitrary one and I constructed an element of the tangent space at the identity that, if it's mapped by J, hits this arbitrary element. So the map is also surjective. In summary, TEG as a vector space is the same as LG. And that was what we wanted to prove. So that shows that these left invariant vector fields, they can be understood by only looking at all the vectors at the identity. Well, that's much simpler to look at all the vectors at the identity than to look at these crazy left invariant vector fields. Okay. However, this LG had this nice additional structure. So this is as a vector space. But we know LG was a Lie algebra if you equip it with the commutator bracket of vector fields. You have left invariant vector fields, you can take their commutator. Now, if we want to equip this one tangent space where only vectors live, here live vector fields, but only very specific ones, but if we want to equip this tangent space with a Lie bracket, we cannot simply take the Lie bracket of vector fields, because a Lie bracket of vector fields needs to eat to vector fields, not only to vectors, but to vector fields, because one acts on the other, but for the one to act on the other one must change from point to point, otherwise it couldn't be derived, roughly speaking. Whereas if I now restrict to these elements, only to these vectors, I cannot inherit this bracket anymore, right? So a remark. L of G equipped with the commutator bracket of vector fields, we already recognized as a Lie subalgebra of the commutator bracket of the Lie algebra of all vector fields equipped with this bracket. And we would so much like to, so I write here like to, would like to, have here an isomorphism of Lie algebras, a Lie algebra isomorphism with TEG. So the isomorphism is already there because the underlying vector spaces are isomorphic. But we also need to have a bracket here. Let me call this also double bracket. We'd also like to have a bracket here such that this isomorphism is compatible with respect to the bracket. Would like to have this here. That is, we need a bracket, double bracket. So the double is only to show it's a different bracket. Double bracket on TEG cross TEG into TEG, such that, and now that's the this is the structure preserving property. So we want this to be an isomorphism of Lie algebras. So we want that if we apply our famous isomorphism J, and we apply it to the bracket of two elements in TEG, we want it to be isomorphic, we want this to be the same as taking the bracket in LG after we mapped the individual elements. Okay, we want this because this is this structure preservation property. So we would like to define a bracket, double bracket on TEG such that this is true, because then we can forget about all this left invariant vector field business and commutator brackets of vector fields. We can forget about all that and only look at the nice and cozy finite dimensional, well, if the Lie group is finite dimensional as a manifold, finite dimensional tangent space at the identity equipped with its innocent bracket. So how do we get such a bracket? Well, the answer is we define it that way. Okay. Define the double bracket accordingly. So how do we do that? Well, we simply say define the bracket of two elements of TEG. I already wrote down from where to where the map goes. Define it to be the bracket of the vector fields, of the left invariant vector fields that are induced from there. And of course, that can only be true if I then this here now lies again in the left invariant vector fields. And this guy here is, of course, supposed to lie in TEG again. So you need to get this back. But that's not a problem because you have J inverse. You pull it back to here and you have it. Okay? Okay, and then you have as a theorem what I wrote down before, what I would like to have, namely that TE, well, then as desired, it follows that TEG with this guy is isomorphic as a Lie algebra to L of G with the commutator bracket of vector fields. So you see, sometimes people ask whether this bracket in differential geometry is the commutator bracket they met before in quantum mechanics. Well, if you do quantum mechanics on a finite dimensional Hilbert space, then you also get kind of commutator brackets and so. Well, at least here on these Lie algebras, this bracket, well, it is not the bracket between vector fields because it's just on a vector space. There's no vector field business here. But at least on the Lie algebra, if it's the Lie algebra of a Lie group, it ultimately comes from the commutator bracket of vector fields, and we have the left invariant vector fields. But you see, this is lots of machinery, but essentially it's all encapsulated here. Okay, so this is this thing, and so next time we'll look more closely at this Lie algebra here, and we'll define in particular something called the killing form. But the killing form is not a form like we defined before. It's not antisymmetric. It's symmetric. It's a symmetric bilinear map. And the killing form tells you a lot about the type of Lie algebra you have. And then you can classify Lie algebras. For instance, there are so-called semi-simple Lie algebras. They can be fully classified. It's a classic result by, I think, Cartan or so, using Dynkin diagrams and stuff like that. Very beautiful mathematics, very important in physics in many places. But then finally, at some point, we'll come to the opposite question. So now we start with the Lie group, and we got the Lie algebra. But what happens if I would first fix the Lie algebra abstractly? I give you an abstract Lie algebra with those and those elements and that bracket. The question is, does there correspond to it a unique Lie group? And the answer is no. There will generically be several Lie groups that have the same Lie algebra. Okay? And then there will be an issue of complex algebras and complex Lie groups versus real algebras and real Lie groups. So the complex algebras you can classify very easily, but very often we're interested in the real ones and in the real groups and so on. And there's lots of there are lots of details to be taken into account. And let me see where I'll take the subject. I'll certainly point out the pitfalls and the wrong assumptions one could make. So we'll certainly develop it to the point that whenever you meet a Lie algebra or a Lie group, you will be able to know there's an issue, let me look it up, okay? Because otherwise we could have an entire lecture on Lie groups and Lie algebras. But we'll certainly stay with the topic for a few more lectures, because finally we'll ask, how does a Lie group act on a manifold? Meaning, say you have the rotation group, how does the rotation group, how can it act on some other manifold and whirl around the points? It's more like physicists think, that there is a group and it acts on something. Okay, how is this action on something? And that will play an important role later on in bundle theory, again, when we look at principal bundles. So there's this whole road ahead of us, and Lie groups play a very important structural role. So it's not only for the applications you know, but also for several applications to come that you should revise this and study this in detail. So see you on Thursday with a continuation. Thanks.